Well, hello everyone. Welcome back to Math with Mr. Naylor. What we're going to do is finish up our Chapter 4 in Calculus by actually going back to a couple smaller topics that are actually found kind of at the beginning of the chapter, but nonetheless, they're new topics for us. And today's topic is the mean value theorem. Now, I have to say, when I was in school, for some reason, when I heard the word mean, I would always think of like mean, but that's not what we're talking about here. Actually, the mean value theorem has more to do with like an average, as we'll find out, kind of more of an average slope. Now, at this point, you should have already had a chance to interact with the sort of common mean value theorem diagram that we went over as a class. But if you didn't get a chance to do that, what we're trying to do is come up with an intelligent statement that relates these, 6 or so words or phrases that directly connects to, again, this handy diagram. Now, what we would see here is that we have a function, that's f of x, but there's a closed interval. And I remember a closed interval just means that there's a beginning and ending point. And we see that if we have a closed interval, there's always going to be able to be a secant line. Now that secant line is denoted with this dashed line, and it turns out that that secant line has a certain type of slope. Now the slope is special because there will always exist a tangent line. There will always exist a tangent line denoted here by the blue that actually ends up having the same slope, or the words that are used here, a parallel slope. So what is it that we notice here? Well, again, there's always going to end up being some point C that has a, where there is a tangent line that is parallel to the secant line, or to add the word slope, where the slope of the tangent line is parallel to the slope of the secant line. You see, the mean value theorem guarantees that this will always happen. Again, that there will always be at least one point C where the slope of that tangent line is parallel to the slope of the secant line. This is kind of your official definition, but the phrases that you guys came up with sort of get the idea, but I would imagine that you want to jot down here our official definition. What's this formula that we see underneath? Once you get the fancy definition, take a look at our formula. It's actually saying the same thing, just with symbols. You see, we have the slope of a tangent line denoted by f prime. Now, it's at C, so it's f prime of C, and that's going to be the same as the slope of the secant line. And I hope that you recognize the f of b minus f of a all over b minus a as the infamous slope formula. All right, so there's always going to be a place where the slope of the tangent is equal to the slope of the secant. So what do we do with this? That's actually a pretty common question. It's a theorem, it's true, but what do we do with it? Well, what we like to do is we like to find the C value that's going to satisfy the mean value theorem. So we're basically going to solve for C. When we're given a function and an interval. Now that's exactly what the two problems are going to look like today. We're going to be given a function, perhaps this function, negative x squared plus 4x plus 1, and an interval. Now when you're given just these two pieces of information, and the directions clearly saying that we want to find C, what we're going to do is we're going to make some slopes equal. And so that's exactly where the problem starts. It starts by finding the slope of the secant. Now, the slope of the secant is actually just good old rise over run, or f of 5 minus f of 1 all over 5 minus 1. Now, I find that the hardest thing for kids with this whole lesson is trying to figure out the numerator. And you just want to remember, when teacher says f of 5, that's simply plugging 5 back into the function. You'll notice that I didn't do anything with the derivative yet. I'm just plugging 5 into the function. And if you do that math, you square it, you multiply it by 4, it apparently comes out to be negative 4. You're also going to do f of 1, and f of 1 comes out to just be regular 4. Now be careful. The formula for slope always says that you subtract these two values. It looks like 5 minus 1 is the number 4. So if you like the number 4, this problem is for you. Negative 8 over 4 is negative 2. Now, what we know is that there's a secant line that connects the endpoints of this interval, and it has a slope of negative 2. Now it's time for the derivative. I should have said now it's time for the tangent, but that means it's time for the derivative of our function. Now, when you do the derivative, what you want to remember is that it's a slope formula. And it would also help to remember that we already know what the slope is. We already know that we seek to have a slope of negative 2. So basically, we want to notice that we're not plugging into the formula, but rather we're setting the formula equal. And when you set a formula equal, you have the ability to solve. Of course, you're going to solve for x. Keep in mind as you're solving this for x that what you're really finding is the c value. And you can call it that if you'd like. You can say that c equals 3. You can keep it as x equals 3. But we just satisfied the mean value theorem. Why? Because we found the c value where the slope of the secant is equal to the slope of the tangent. Except the fun's not quite over yet, because for these types of problems, I always ask students to make a sketch. A sketch of what, you say? Well, a sketch that shows that you understand what's going on here. And so the neat thing about these sketches is that they always contain about 3 things that are the same. They always contain the function. Now I'm just saving a few seconds here, and I'm showing you a sketch of the function. But just so you understand, I probably would have used my calculator to draw that negative x squared plus 4x plus 1. Next, you're always going to show the endpoints. You're going to show the endpoints of the interval. And that then will always create a secant line. If you would like, you can make it dashed, you can make it solid. I like to make it dashed just so it looks a little different. So there's our secant line. And by the way, that secant line, remember, it had a slope of negative 2, just so you remember what's going on from the problem. And then last but not least, probably the most important part of the problem is to show the c value, or the x value where your tangent line is parallel. Now, it's just a sketch, and so honestly, you don't really need a calculator to put all the lines in. In fact, you might realize you don't actually know enough information about these lines to really put them in the calculator. All you really know is the slopes are both negative 2, and this occurs at the c value or the x value of 3. So that's what I want to see in your sketch every time. There's always a sketch that goes with the mean value theorem. Ready to try one? Okay, well, that's what we normally would have done. I would have given you this problem to try, and you can see if you can satisfy the mean value theorem. That is, can you find c? So if you're still watching, you should be trying this problem. So go ahead, push pause on the video. All right, now if you followed my example from before, you would have found the slope of the secant first. Yeah, did you notice that we actually don't do the derivative first? I actually recommend that you do the good old secant slope first, because it kind of reminds students that you need this number. And so before I do the derivative, I'm going to carefully set up my f of b minus f of a, and then, of course, b minus a. Now, you would have had to put the number 5 in your calculator. That's fine. Actually, when you put the number 5 in there, you get 1.373. Make sure you're in radians. When you put 0 in your calculator, it just comes out to be 0. So I'm not going to show that. And then all over 5. So we end up with 0.27. Now, what's 0.27? It's the slope of the secant. So now it's time to find the derivative. the derivative of inverse tangent. Oh, the derivative of inverse tangent. No, it's not secant squared. That's the derivative of tangent. Oh, it's a formula. Right. Did you look back at your notes for the formula? Well, I'm going to share with you that soon, that is in the second half of the year, we're going to be doing these formulas backwards. So it's not going to be too bad of an idea if we kind of remember some of the formulas from the first half of the year forwards. All right, so 1 over 1 plus x squared. Now that's the derivative, and according to the mean value theorem, you basically want that derivative to equal the slope of the secant. You want it to equal 0.27. So now we have ourselves a little equation to solve. There's different ways to solve this. Some students would multiply the denominator over to the other side. There's nothing wrong with that. I kind of want to share that when you're in a situation where you have like a fraction equal to a number and your variables in the denominator, did you know that you can do the reciprocal of both sides? If you do the reciprocal of both sides, you get 1 plus x squared over 1, and then you get 1 over 0.27, which on a calculator, you can turn that into a little more of a regular looking number, about 364. So just saying, I can do the reciprocal of both sides. I get my x squared up to the top, so that x squared is, let's write that a little bit better, x squared is equal to 264, and then I can take the square root of both sides. Now, when you take the square root of both sides, you do get plus or minus. Did you remember the plus or minus? Let's talk about that in our sketch. You say, our sketch? Yes, there's always a sketch that goes with one of these problems. Now, when you finally do one of these on your own, you're going to have to graph the function. It's an inverse tangent. It doesn't graph super nicely on your calculator, so I'm going to kind of help interpret it a little bit. This is your inverse tangent graph. Maybe you remember it from last year. We want to put our interval or our endpoints on the graph. I'm not going to make you label those necessarily, but you should know that they're at 0 and 5. Okay, there's always a tangent line, a secant line, but yeah, there's going to be a tangent line that's also parallel to this. Now, did you notice that the C value, 162, did not come out right in the middle of both of these of your interval? Did you think that it was always going to be in the middle? Well, I want to let you know that not necessarily. It's definitely between 0 and 5, but it's certainly not right in the middle. It's actually skewed slightly to the left, is it not? And I'm going to try to draw it looking just the same. So I end up with 162. I do want you to label that one because I want to know that you know that that's the C value that satisfies. So what about the plus or minus? You might notice that technically for my drawing, the minus doesn't appear to be valid. In fact, I really should only have positive 162. But I just want to share with you that if we needed to, we could have said that at negative 162, that we also have a tangent line that's parallel. So I say if we needed to, we don't need to because the interval, it's outside of the interval. But the truth is that the negative 162 does visually still create a tangent line that's parallel. But I am going to erase it from my sketch because it shouldn't be on this one since I'm only going from 0 to 5. So the mean value theorem, do you remember what it says? Well, you're going to want to because it's actually a test question. You want to be able to say the mean value theorem in your own words because there's always going to be a point C, right? On a closed interval, there's always going to be a point C where the slope of the secant is parallel to the slope of the tangent.